Now, as you see from the preceding video and the whole example, it can get fairly complicated interpreting all these things if you're not aware of the rules. Just like playing a board game without knowing the rules. Okay, if you get any good at a board game, you've done something every bit as complicated as understanding these rules. And the basic two rules, the only two rules really that we used here, are that the work done by the net force on a system is equal to the change in the kinetic energy of the system, and the change in kinetic energy is equal and opposite to the work done by conservative forces on the system. These are basic definitions, and they're definitions that nobody seems to ever be able to tell me when I ask. So I hope that we're getting to the point where you understand, where everybody understands, that these definitions are a starting point. They're kind of a place that you can just grab onto and proceed from. They're always true. You just have to know how to use them. They're easy rules once you get used to them. And of course, you need a lot of practice interpreting different systems and different situations in terms of the rules. Okay, so you can't just do what you think you ought to do. I mean, it's great you have an opinion about what you think you ought to do at any stage, but you have to check your opinion against the rules. Now, to help sort this out, it can be very helpful. A lot of people find it very helpful to map things out. So we're going to map things out. First of all, net force. Well, net force can be broken down in various ways. There can be various types of forces acting on a system. One of the most fundamental ways to break it down is forces that are conservative, forces that aren't conservative. It's got to be one or the other. Or as I say, a force could be a mix of both. And you'd have to deal with that, putting some of it into the conservative and some into the non-conservative category. And then conservative forces. There are lots of different kinds of conservative forces. Gravity is conservative. Ideal elastic force is conservative. And there are many other conservative forces. I could expand the list to magnetic, electrostatic, many other types. Okay? So, we can always draw a map of this nature, and remember that any triangle on a map means that you can find any of the quantities, any of the three quantities, if you know the other two. So any two quantities that you can know, you can always find a third. Another way of saying the same thing. Now, if this is so, then the work done by the net force over some interval of position or some interval of time, work done by the net force has a similar relationship to the work done by conservative and work done by non-conservative forces. Now, what's the relationship between net force, conservative forces, and non-conservative forces? Well, the net force is the sum of all other forces, meaning the net force is equal to the conservative force plus the non-conservative force. So the work done by the net force is equal to the work done by the conservative forces plus the work done by non-conservative forces. Also, the work done by conservative forces can be said to be, it is equal to the sum of these three now. The work done by gravity, work done by elastic forces, and work done by other conservative forces. You can always have this other, okay? You can list the conservative forces you know something about, and then you say, well, there are others that aren't specified, but they got to be included in the calculation. So if we know these two, it's not enough to get this one. We'd have to know all three of these to get this, or if we know this, and any of the two of these, we can get the third. This is not a triangle. It's not quite as simple as a triad, but we should be able to understand what this picture is telling us.